All right. All right, everyone. So homework 17 due next Monday, the 19th, and I'll check them off and give you 10 points. So that will help towards your grade. So lab report. We have 2 lab reports I'd like for you guys to upload to Canvas. One is on the problem set. So work on that. That actually was really covered our last exam. So really it's not going to cover anything in test 4. But make sure you upload that, and also upload the lab report on spontaneity for those of you that did that. I think there were about 3 of you who did that last Friday, so make sure you 3 turn in that lab report so I can give you points. So our last quiz is going to be due on April 26th. I believe that's the last day of class. That's a Monday. So, it's all going to be online. So this is the last day of class. And if you're happy with your 3 quiz scores, I dropped the lowest quiz. I have not graded quiz 3 yet. And I don't know if my work study student will grade it, but I'll try to get those grades, quiz 3 score, back to you as fast as I possibly can. Anything else? Update your lab notebook. I'll give you 100 points if you turn that in at the last day of class. So homework and your lab notebook should help boost your grade. Another thing that will boost your grade is this clutch prep. If you paid the $30 or so, please make sure you do all of those exercises. Again, this will probably help you, not so much with the class, but for your future coursework, because there's a lot of pre-medical students and pre-PA students. Whatever it may be, whatever your circumstances are, if you do everything on clutch prep, I'll give you some extra credit when I compute the final grade. Can you guys think of anything else? Joshua, you think of anything? Okay. All right, so that's what we are going to do. We'll try to finish chapter 17 this week. Chapter 17, we were talking about this concept of entropy. Okay, remember entropy? Entropy basically means disorder. Okay. And actually, this is something that is different than the other thermodynamic parameters. The other thermodynamic parameters, if you remember, are delta H, which is a measurement of heat, and this big one here, delta G, which is Gibbs free energy. This is the final judge, whether the reaction will proceed. Gibbs free energy. And then this is enthalpy. This is from Chem 1. This is whether a reaction will produce heat or whether a reaction will require heat. So these are the 3 big terms in thermodynamics. And this is delta H, delta G. Disorder or entropy can be a delta S, but it can also be just plain old S. Okay, just plain old S. Just realize that. Well, these guys usually in our textbooks we have them as delta H or delta G. Okay, change in final minus initial. Final minus initial. S has some values here. Okay, we do not memorize any of these numbers. I will never make you memorize numbers or constants or any of that sort. But 2 things I want you guys to recognize here. One is look at this here. Just look at the units. So we got some units here for S. Okay, joule over Kelvin mole. But also look here. I want to bring your attention to this S, but it's not just S. See, we have an S and a superscript. Okay. Okay, this means standard state. Okay, this is actually called S naught. S naught, delta H naught, delta G naught. That naught, which is basically a superscript O, superscript letter O, superscript, this means standard state. So what is standard state? What is standard state? Well, it's a very specific set of conditions. You know, chemistry is all about reactions. But if we're going to do a reaction at 25 degrees C, if we're going to do a reaction and it involves gases, if the gases have a pressure of 1 atmosphere, if we're working with solutions, you know, solutions of a concentration, the concentration, if it's 1 molar, that is how we define standard state. And we look these values up in some textbook. In fact, your textbook has all the standard state values, right? Okay. All right, so standard state, just realize that, yes, there's standard state, and those numbers are given to us in the textbook. Also recognize this equation. I talked about this on Friday before the weekend. The equation is delta G, equals delta H minus T delta S. But there's also the other version, and the other version is the standard state version. Delta G naught. Anytime you see that naught, that superscript O, I just want you to realize that we're talking about a very specific set of conditions, and those set of conditions are called standard state. All right, so standard state conditions. So this and this are not the same. Okay, this is standard state. This is any other whatever temperature, whatever pressure if you're talking about gases, whatever concentration if you're talking about solution. Remember, solution is solute plus solvent. And we look these values at the back of the book. All right, let's do some practice problems together here. What is the entropy change? Change means delta S for the following processes. And remember, entropy stands for delta S, and entropy also means disorder. Okay? Disorder. All right, first one, A, condensing water vapor. So what is condensation? Condensation, if we remember, is a gas going to a liquid. Okay, knowing that a gas goes to a liquid, is that more disorder or less disorder? Less disorder. In other words, more order. Remember, the gas molecules are all over the place. The liquid molecules little bit more organized. So here I'm going to say the delta S is negative. Remember. Okay? If you're negative, you're tending towards order. If you're positive, you're tending towards what? The opposite, disorder. Okay? Again, let's look at our kitchen sink example. Okay, did you guys clean your kitchen sink yesterday, before or after dinner? Okay. You guys cleaned it. And what do you think is going to happen tonight? Okay? It'll be a mess, dirty. Okay? That's positive entropy. More disorder. How about this one? Forming sucrose crystals from a supersaturated solution. Okay, anytime you see crystals, crystals are the epitome. They're very, very ordered. Okay, they're super ordered. Okay, in fact, crystals. In fact, the more ordered the crystal is, the more, like a diamond, the more valuable it is. So forming sucrose crystals from a solution is solute plus solvent. Crystals are, they're more ordered than a solid. Some crystals are. So this is definitely negative. Okay, this is, you're forming crystals, you're making something that's very ordered. So yes, the entropy, change in entropy is going to be negative. How about this one? Heating hydrogen gas from 60 degrees to 80 degrees. What do you think happens when we heat something? The molecules move more. So is that more order or more disorder? That's more disorder. So will the delta S be positive or negative? Positive is the right answer. Very good. Okay. So if you heat something, molecules have more, and they experience more states. Okay. They experience more freedom, more motion, however you want to think about it. More disorder. Okay. How about sublimation of dry ice? Sublimation. What is sublimation? Anybody remember? Sublimation is a solid going straight to a gas. Okay? Sublimation is a solid going straight to a gas. So if a solid going straight to a gas, skipping the liquid phase, is that more order or more disorder? More disorder. So more disorder, is your entropy going to be positive or negative? Positive. More disorder, positive entropy. So let me just remind you guys, more disorder means a positive entropy. Positive entropy, delta S greater than 0. All right, how about this one? Same thing here, but we'll work with an actual reaction. Okay, what is the entropy change here? We're going to ask whether it's positive or negative for the following reactions. All right, we have here a solid going to 2 molecules of a gas. Okay, solid going to a gas. So positive entropy or negative entropy? Positive entropy is the right answer. So either you can say delta S is greater than 0, okay, going from a solid to a gas, or you can just write here positive. More entropy in part A. What about part B? We have here, let's see if we can zoom it in here. We have 2 molecules of a solid, 1 molecule of a gas. Maybe I'll say 2 moles of a solid, probably better. 1 mole of a gas goes to 2 moles of a solid. So look here, we have 3 molecules, 2 solid, 1 gas, 3 molecules going to 2 molecules. Those 2 molecules or those 2 moles are a solid. So more order or less order? More order. Everyone see that? We're going from 3 to 2. 3 to 2, not only that, we're producing a solid. So everyone agree that this is going to be negative? Okay, negative. So here we're making more order. This is the more order. So this is really what entropy is all about. Entropy along with enthalpy come together along with temperature to determine whether a reaction is going to proceed in the forward direction or not. All right, part C is a little bit of a tricky question. Part C, we have 2 molecules, diatomic nitrogen gas, 2 atoms, and we have 2 moles, 2N and 2O here. The answer to this one is cannot tell. Okay, so cannot determine. Why is it cannot determine? Because right, one gas. We have 2 gases. So 2 gases on the reactant side, 2 gases on the product side. 2 goes to 2. There's gases. We really don't know. So I'm going to write here cannot determine. Right? Okay, so cannot determine. So don't just think, oh, it's going to be positive, oh, it's going to be negative. Really, this one, it's not overwhelming. Once again, because 2 atoms of nitrogen, 2 atoms of oxygen go to 2 atoms of nitrogen and 2 atoms of oxygen. We have 1 mole here plus 1 mole here equals 2 moles on the reactant side. We have 2 moles on the product side, 2 and 2. Gases forming gases, cannot determine. Right. Couple of notes for you guys. For a spontaneous process, we are looking for delta S to be positive. Okay. Delta S to be positive. And for an equilibrium process, the entropy of the universe, which is systems and surroundings, has to equal to 0. All right. And don't forget, we're having systems and surroundings. The system, as a reminder, is just the reaction, not even the beaker. The beaker is the surroundings. The test tube is the surroundings. So just be aware of these 2 scenarios. And then another thing I want you guys to recognize, now I'll give this on the exam, but it's best that you just have this in the back of your head or in your toolbox. This is the delta S of a reaction. Okay, delta S of a reaction. And it's the products, sum of the products minus the sum of the reactants. I don't know if you guys remember this, but we have the same thing for delta H. We did the same thing for delta H. If you guys remember from Chem 1, it's the standard state of the products. We add them up, products minus the sum of the reactants. Okay, this M and N just means the stoichiometric coefficient. Okay, the stoichiometric coefficient. So we did this in Chem 1. We will see this in our next chapter. There's a delta G of a reaction, which is the delta G of the products minus the delta G of the reactants, each multiplied by the stoichiometric coefficient. That's what M is. That's what N is, the stoichiometric coefficient. Let's talk about this here. Okay. So delta H, delta G, delta S. What does this little symbol mean? It means what state? Standard state. It means standard state. So this is the standard state enthalpy of the reaction. This is the standard state Gibbs free energy of the reaction. And this is the standard state entropy of the reaction. So let's calculate the delta S of a reactions for some of these guys. All right, it's going to be products minus reactants. All right, so for this, I'm going to give you the S here. Okay. So this, I'll give you this value for S. So for the S for CO2, again, I'll give you this on the exam. You do not memorize it. The S for CO2 is 213.68. The units are joules per mole Kelvin. Again, I will give you this. Okay, it's not something you need to know. The S for O2, okay, standard state. I looked this up before we came here. And that is 205.03 joules per mole Kelvin. And then what else is missing here? The S for CO. The S for CO is 197.90. Carbon monoxide, okay. So these are values that we get from the back of our book. These are values that I got before I came to class. And with that, the entropy standard state for CO2, the entropy standard state for O2, the entropy standard state for CO. So once you have those numbers, which will be given to you on the exam, we can go ahead and use this equation and solve this. Let me shut off the lights here. Let's read this again. Calculate the standard entropy change, delta S of the reaction for the following reactions. Okay, so products minus reactants. Okay, so what's our product here? CO2. This is for 1 mole, but how many moles do we have? 2. So it's going to be 2 times 213.68. I'm not going to put the units in. I'll put them in later. Okay, so sum of the products minus, a lot of students mess up on the algebra here, minus the sum of the reactants. O2 is 205.03. Once again, I'll give you these numbers on the exam. Products minus the reactants, so reactant O2, and then plus CO, we got 2 of these, so we got to multiply it by 2. 2 times 197.90. Where students get a lot of mistakes is they forget to multiply. So you got to multiply by 2. And you got to multiply by 2 here. Products minus reactants, yeah. All right, doing this on my calculator, make sure you do this on your calculator properly. Also, calculator errors is common here. And doing that on my calculator, I'm getting an answer of minus 73.47 joules per mole Kelvin. Okay. All right, what does the minus sign tell you? More order or more disorder? More order is the right answer. Okay, that's what the minus sign tells you. Or how about this one here? 3 O2 gas goes to 2 O3 gas. So let me give you the entropy standard state for O3 gas, and that is going to be, again, I will give this to you, and that is going to be 238.82 joules per mole Kelvin. Products minus reactants, we sum them up. So here's our product, O3 gas. It's this value that I just gave you is for 1 mole, but we got 2 of these, right? So what do we need to do? We need to multiply it by 2. So it's going to be 2 times 238.82. I'll put the units here this time around. Minus, put that big bracket in, minus O2. Here we got the entropy, a standard state of O2 is 205.03. but we see we got to multiply it by 3. Okay, right? Everyone see that? Because the value here is for 1 mole, but in the balanced equation we got 3 moles. So we got to multiply it by 3 because we got 3 moles. So 3 times 205.03. And doing that on my calculator, I am getting minus 137.42. Okay, so double check my math. Joules per mole Kelvin. What do you guys think that minus means? More order. Okay, very good. More order. Well, you're going from 3 molecules to 2 molecules? Yes, that's more order. 3 molecules to 2 molecules is more order. All right, let's do one more problem like this, and then we'll move on. Okay, our last problem here. Let me give you some numbers here. Calculate the delta S of this reaction. Standard state. Okay, standard state. If it's not standard state, these numbers, I can't get you the numbers from the textbook if they're not in standard state, because the textbook gives you standard state numbers. All right, so before we move, let me give you some of these numbers that I got off the book. The entropy at standard state for NaHCO3. This is called sodium bicarbonate, by the way. Sodium bicarbonate. And that's going to be 102.09 joules over mole Kelvin. Okay. And then the other one I need to tell you is water liquid. Not water solid, but water liquid. And water liquid is going to be 69.9 joules per mole Kelvin. And then the other one that I need to tell you is sodium carbonate. And sodium carbonate is going to be 135.98. Like I said, we look these numbers in the back of the book, and then once we have that, we do our math. Products minus reactants. Sum of the products minus sum of the reactants. Okay, don't forget to multiply this by 2, that value for NaHCO3, because we have 2 moles. The number in the back of the book is for 1 mole. Okay. And like again, I'll give you these values. All right, so products, Na2CO3, is going to be 135.98. I'll put the units here, joules per mole Kelvin, plus water. Water is 69.9 joules per mole Kelvin, plus CO2. CO2 from our previous problem is 213.68. joules per mole Kelvin. Okay, that is our products. Okay. Minus the reactants. Minus, put a big bracket here. Minus your reactants. Well, we only have one reactant, and that's NaHCO3, and that's 102.09 joules per mole Kelvin. Don't forget to multiply this by 2. Okay, a lot of students forget that in the stress of the exam. Okay, multiply this by 2. And It's products minus the reactants. Another thing I've seen is people switch it. It's products minus reactants, not the other way around. All right, doing this on my calculator, I'm getting 215.3 joules over mole Kelvin. What does the positive sign tell you? More order or more disorder? More disorder. And you kind of see that? All right, just look at this with me. We have a solid here. Okay, solid, very, very ordered. Okay, but what are we making? We're making 3 molecules. One of them is a solid. Okay, fine. Liquid is very disordered, and a gas is super, super disordered. So we're making things that are disordered. We're making states that have more space, more motion, more degrees of freedom. So it makes sense. We just have to attach a number to this. The number's 215.3 joules per mole Kelvin. Here's a relationship for you guys. This is the delta S of the surroundings. Okay, delta S of the surroundings. The surroundings is everything that is outside the reaction. So even your beaker is your surroundings. If your surroundings get hot, your test tube gets hot. Okay? If your test tube, your beaker, everything. The only thing that is your system are the molecules inside the beaker. So that's related to the enthalpy of the system. That is your reactants, that is your products, divided by your delta T, divided by T. Here, T is temperature. Okay, T is temperature. I think a student asked me, is this temperature or time? It's temperature, number one, because temperature has a capital T, first of all. And number two, the equation, delta G equals delta H minus T delta S. What determines whether a reaction is going to proceed is temperature, not time. Okay. It doesn't matter if the reaction takes place within an hour or a month. Okay, it's going to happen. Not worried about time. The major influencer is temperature, just like delta H is and just like delta S is. So make sure you are aware of that relationship here. Delta S, entropy of the surroundings, is related to the entropy of the surroundings, is related to the enthalpy of the system divided by temperature. So let's say you have an exothermic reaction. Say you have an exothermic reaction. You see, in an exothermic reaction, the delta H, we'll call it the delta H of the system, is going to be negative. Okay? So the negative with the negative is a positive. So the delta S of the surroundings become positive. Okay? If you're exothermic, what are you releasing? You're releasing heat. Who gets that heat? The surroundings. What happens to the surroundings? Get more order or less order? Less order, right? If I blow at the surroundings, okay, the surroundings get more disordered. It's not like all those air molecules are going to be nice and organized, and it's not like I'm going to, the surroundings are going to fight back. No, okay, so you release heat, the surroundings take the heat, the surroundings naturally become more disordered, okay? Right, there's something called the Third Law of Thermodynamics, and that is, this is something I don't know. Again, more interesting stuff. The entropy of a pure crystalline substance is 0. Okay, at absolute 0. Okay, at absolute 0. What is absolute 0? Absolute zero is when your temperature in Kelvin is equal to 0. Okay, that is when all molecular motion ceases. So pure crystal, 0 molecular motion. Okay, the key word is pure. I don't think in nature, I guess we can look this up on the internet. I don't think there's something called a pure crystal. Most crystals, and again, I won't test you this, but a pure crystal, everything is ordered, nice and neat, like perfect as perfect can be. But that would be a pure crystal. Molecular motion is 0 at 0 Kelvin. But real crystals have something where a little bit of disorder, not a lot, but you see here, like bricks in a brick house, some of the bricks are a little bit off. Okay, that's still a pretty good crystal, but it's not like perfect crystal. So that's called Mosaicity. I'm not going to test you on this, but Mosaicity. You ever read The Double Helix by James Watson, Francis Crick, where they crystallized DNA and they had to figure out the structure of DNA when they crystallized it? The problem with crystals is that mosaicity. So when you hit it with the X-ray, you won't get very good diffraction. A pure crystal like this, perfect, like bricks in a brick house, perfectly aligned. They will have 0 motion at 0 Kelvin, but they're very, very good at getting the structure. Okay. Anyways, just an interesting aside. Nothing I'm going to really test you on. All right. So pure crystal. A crystal is very, very ordered at 0 Kelvin. Perfect order, there's no motion. All molecular motion ceases. All right, let's talk about Gibbs free energy. This is it. Okay, Gibbs free energy is the final judge. Okay, the final judge. Remember our fundamental equation, delta G equals delta H minus T delta S. Well, delta G decides. Okay, it's decided. Is this reaction going to move towards the products, or will the reaction stay in the reactant side? Okay, so this is the final judge. Yes, it takes input from enthalpy. It takes input from entropy. We just studied entropy, measurement of disorder. And some reactions, if you increase the temperature, the reaction moves forward. In some cases, if you decrease the temperature, the reaction moves forward. All of these 3 variables, you see, delta H, T, delta S, ultimately will determine delta G, which is the final judge in determining whether the reaction moves forward or not. And if a reaction moves forward or not, we usually give it a negative sign. We call that an exergonic reaction. Exergonic. And then if delta G is positive, it requires energy. This reaction is a no-go, unfortunately, and this is called an endergonic reaction. Endergonic. Okay, by the way, Gibbs free energy is energy that is useful, energy that can be harnessed. So delta G, or delta G naught if we're talking about standard state conditions, is energy that can be harnessed. Energy that can be captured, energy that is not lost. Usually heat is lost. Okay. Energy that is not lost. heat is usually lost. Heat is what I'm going to call lost energy. We really cannot capture the heat. All right, same equation as before. Delta G of the reaction is sum of the products minus sum of the reactants. Okay, we look these in the back of the book. Also here, I'm giving it to you in standard state. Okay, don't forget that not symbol. Okay, not. That means standard state. Again, just as a reminder, 25 degrees C, 1 atmosphere if you're talking about gases, and if you're talking about a solution, which is solute plus solvent, it's 1 molar. All right, remember delta G negative, that's what we're looking for if we want a reaction to go. Thumbs up. When I say thumbs up, it means the reaction is going to move towards the positive side. Product side is going to move towards the product side. The delta G is going to be negative. Okay, it's either delta G or even at standard state. If your delta G is equal to 0, the reaction doesn't go. Okay, the reaction, I will say this, it's like 50-50 reactants and 50-50 products. Okay? So really there is no change in the reaction. This is also called an equilibrium constant of 1. Okay? If we're talking about an equilibrium. Remember equilibrium constants, everyone? And this negative delta G would mean an equilibrium constant greater than 1. Okay, remember equilibrium constant, if we had $1 million, are we moving forward in life or backwards? If we had $1 million, we would move forward. The larger K is, capital K, the more forward the reaction is moving towards or favoring towards. And then finally, if your delta G is positive, we call that an endergonic reaction. And here the equilibrium constant is small, okay, 10 to the minus 10, 10 to the minus 5, 10 to the minus 20. Very small equilibrium constant. Reaction is not moving forward. It's kind of staying in the reactant side. All right, this is the last bit I'll lecture on today. So remember here delta G naught equals delta H naught minus T delta S. Okay, we can also say the same thing for non-standard state conditions. And I went over this on Friday. I don't know if you guys remember. If your delta H is negative, that's enthalpically favored. If your delta S is positive, that's entropically favored. So it doesn't matter about the temperature. Okay, you're always spontaneous. Your delta G is always negative. Okay, this second one is the opposite. Delta H positive is enthalpically disfavored. Delta S negative, entropically disfavored. It don't matter. Okay, no matter what temperature you're at, the reaction is not going to proceed. All right, these last two are a little bit tricky. Okay, here it depends on your temperature. Here's a reaction that's entropically favored, but enthalpically disfavored. So again, you look at your temperature. Okay, here we want to raise the temperature to make it go forward. And then finally, here's a reaction that's enthalpically favored, but from a standpoint of entropy, it's disfavored. Okay, the triangle means it's disfavored. Again, like before, we got to look at the temperature. Here, we got to lower the temperature to make the reaction move forward. All right, so this was a reminder of last Friday's class. All right, everyone, thank you. I'll see you all on Wednesday, and start working on your Chapter 17 homeworks and your Quiz 4. All right, I made videos of Chapter 17 problems, so you can use them if you run into any difficulties.